Hello everyone, my name is Qazi Tahasin Mahmood. I am a graduate student at the Department of Mechanical Engineering at the Wayne State University. My supervisor is Dr. Muhammad Arif Hassan. Today I will be representing my research studies on the classical analogous quantum superposition of states. In the modern age, for the study of quantum information science and quantum computing, superposition of states is an essential topic. The superposition of states is the quantitative connection that is formed by the superposition of the former states. The higher number of pure states will result in a higher number of superposed states, and the correlation between the subsystem can create through entanglement makes an essential tool for information processing. More possible states mean more possibilities for data acquisition and processing. We can use the superposition of states for the demonstration of the Berry phase. Berry phase is the phase difference that is accumulated over an adiabatic cyclic process which is in the parametric space of Hamiltonian. This is a good demonstration of the quantum phenomena which can be expressed through the classical system of Foucault pendulum. This system was introduced first for a cyclic process, but later it was derived for the non-cyclic system. We have demonstrated the Berry phase formation in the elastic bead for both linear and nonlinear system at variety of driving parameters of the granular beads, and later we have used the Berry phase in order to demonstrate a mass sensor that acts on the coherent superposition of states. So what is the motivation of our work? Previously, the basic purpose of the study of the classical analogous superposition of states to study about the topological quantum computing, where the topological properties of the elastic granular beads which are driven harmonically and different driving conditions can demonstrate various topological properties. Previously, these coherent states were not sustainable. Because of that, environment can quickly destroy these delicate coherent states. Because of that, absolute zero temperature were required to observe the delicate coherent states. In our study, this absolute zero temperature is not required due to the elastic beads. We drive the granular beads harmonically and explore different topological properties in the environmental temperatures. While the linear system shows the quantum phenomena, to observe it true quantum phenomena, the system must show nonlinearity. In our research, we have shown both theoretically and experimentally the nonlinearity of elastic system that is formed by granular beads and driven harmonically. As our system is highly adaptable to the external excitation, different combination of amplitude, force and frequency can show us different nonlinear system. Later, we have explored our system to study the Berry phase. Previously, the Berry phase used to be studied in a cyclic environment. We have studied the Berry phase in both cyclic and non-cyclic environment using the coherent superposition of states by driving the granular beads in different combination of forces. And later, we have used this Berry phase to formulate a mass sensor. Previously, different types of mass sensor like quartz crystal microbalance or bulk acoustic wave resonator were used to study in the mass sensor, but there are some problems with the existing mass sensor, like the sensitivity of the quartz crystal microbalance depends on the crystal thickness, which decreases the sensitivity of the increase with the increase of the thickness, and the bulk acoustic wave resonator depends on the temperature of the system and also in the acoustic wave velocity. So in order to advance to our research studies, we need to know what is the binary bit and the quantum bit. A binary bit are used in the classical computers to operate the mathematical modeling. The binary bits have two distinct states, 0 and 1. If we want to express these distinct states with the spin, we can show it in an up spin and down spin position. So binary bit will have only two of the spins, like up spin that we can see in the left and the down spin that we can see in the right. But in the quantum bit, which are used in the quantum computers to operate the complex computations, we have multiple distinct states like E1, E2, E3, E4 that is formed by the two distinct states of the binary bit. If we form this, we with the two of the binary bits, we can have four of the distinct states, which can represent four of the spins, like up spin for the case of the E1, down spin for the case of E2, up and down spin for the case of E3, and down and up spin for the case of the E4. So we can get a total number of four distinct states with just two of the binary bits. Now let's in order to make form those quantum bits, we can start from a simple demonstration of a single mass linear system. So we consider single mass spring system. So, and if we want to just express it through a equation, we have m u1 double dot equal to minus k u1. So a single mass spring will have only of the one natural mode oscillation. What does a natural mode of oscillation means? This means that the system itself, if we give some initial condition to the system, it will vibrate only on the one of the frequency, that is the natural frequency, and we can just get it through some mathematical calculation. The natural frequency will be omega equal to square root of k by m. We are connecting this one mass with only of the one of the spring, but if we can connect the masses with two of the springs, with the calculation we can get the natural frequency of the system as omega equal to square root of 2k by m. We will say these are the eigenmode frequency, as the system will have in the later we will see that in the system will have exactly pure state in those eigenmode frequencies or in the natural frequency. Now if we move to the two mass spring system, we can formulate the equation of the two mass system. So how we solve this two mass system in order to get the natural frequency for the mass spring system or the eigen mode of the system. So if we take the compact ancest for the system as u1 equal to a1 exponential of I omega t and ut equal to a2 exponential of I omega t, if we just find out the stiffness matrix from the system and the determinant of the stiffness matrix, we can get the natural frequency for the mass spring system. We have two of the natural frequencies, omega 1 and omega 2. In the top figure we can see that the omega 1 is the in phase mode, as both of the masses are moving in the same direction at any instances. So this is one of the eigenmodes, that is omega 1, and in the second figure we can see that the masses are moving in the opposite direction at any instances. So this is our second eigenmode. That means it is the omega 2 which has the out of phase mode. And in the third figure we can see these are the combination of both of the modes that we will later show how we form this and formulate the two mass spring system for the combination of those masses. So we have this natural mode eigenfrequency that depicts the pure states. So we have two of the pure states that we are defining as E1, which is the 1 by square root of 2 1 1 mode, and another pure state as E2, which is 1 by square root of 2 and 1 minus 1 mode. These are the two pure states for our system. So now we can see the in phase eigenmode and out of phase eigenmode into how we can visualize it in a time manner. So we take this system, so we have two of the system and we are driving one of the masses. So the left mass we are driving the system with f1 exponential of I omega t. That means we are driving it with the amplitude and a frequency. So if we drive the system in their two eigenmodes, that means the frequency will be omega 1 and omega 2. We will get the two in phase eigenmode and out of phase eigenmode. So we can see in the left the displacement is we have the highest amount of amplitudes, and the masses are moving in both in the in phase mode or at the same point at every instances. But in the second figure we can see that for the out of phase eigenmode, the masses are moving in the opposite direction. That means one mass has a negative amplitude and one mass has a positive amplitude. That gives us the phase difference of pi, which is the out of phase eigenmode. And in case of a coupled motion of the masses, we drive the system with another frequency. That means if we drive the system any other frequency other than the two eigenmodes, we will get this coupled motion. So we can see one of the masses has highest amplitude and another one of the masses has lowest amplitude. With the change of this the frequency, we'll get two different types of coupled motion of the masses, and with that we can get different types of responses in the two mass spring system. Now we are working on a numerical simulation of this coupled mass spring system. As it is easier for us to formulate the theoretical calculation of the two mass spring system, but when we move to a higher masses like 3 mass, 4 mass, the numerical theoretical calculation will be much harder to implement. So we move to a numerical system where we solve the numerical system through the MATLAB OD45 command, and for that we start working on the numerical calculation of the coupled mass spring system. So here the same calculation is done for the case of the two mass coupled system. So we in order to get the eigenmode frequencies of the system, we apply no external excitation in the system, and we apply some initial condition to the first mass. So if we then just do the numerical calculation, we can see that there are two of the eigenmode frequencies that we can find. Here at the first one, we can see the first eigenmode frequency is the omega 1 is at 1, and the second eigenmode frequency omega 2 at a square root of 3. This is the same we can get from the theoretical calculation, as a stiffness of the masses and the weight of the mass. We can take it as in 1, and we can see the two of the eigenmode as same as the one that we can get in the numerical calculation. And over here we can see that the first eigenmode omega 1 equal to 1, where we can see the phase difference at that time is 0 in that particular frequency. And when we move to the second eigenmode frequency omega 2 equal to square root of 3, we can see the phase difference is pi. So the first one, when the phase difference is 0, depicts the in phase eigenmode, and the second one when omega 2 phase difference is pi, so then the system is at out of phase eigenmode. Now if we sweep the frequency, that means change the external excitation frequency from 0.5 to 2.5, we can see how the phase difference of the system moves. So as we can see, when the system is 0.5 to first eigenmode frequency 1, then the masses move in the in phase mode. That means the phase difference between the masses is 0. After the eigenmode frequency 1, the phase difference between the masses starts to increase up. So there is some phase difference it creates over here, and at the exact moment of omega 2, so omega 2, that means square root of 3, the frequency is square root of 3, then the phase difference between the masses is at pi, and after that it continues. So we can see the both of the changes with the both of the phase difference changes omega 1 omega 2 in the if we sweep the frequency over here, and this can be made much more sharper if we can choose the change the damping of the system, as the damping of the system has effect on the how the masses moves in through the frequency range. Now we move to a coupled mass chain system where two of the masses are coupled in along the chain, and other two masses are coupled across the chain. The equation of motion for these cases that we have over here, where we are driving the first mass of each of the chain, the left one and the left u1 displacement mass and v1 displacement mass in two of the chains. In order to get the eigenmode for this system, we apply the same condition. We don't apply any external excitation in the system, and we apply initial condition for the mass only for the mass one. And if we apply that one, we can see that there are 4 of the eigenmodes. So the first eigenmode is around 1, the second eigenmode is around square root of 3, third one square root of 3, and fourth one is at 2. And with that we can get the total 4 number of combination of the eigenmodes. So when all of the masses are moving in the same direction, 2 of the masses are moving in the same direction, and along the chain are moving in the same direction, but the other one where the along one mass is along the across the chain, they are moving in the out of phase mode, and vice versa for another eigenmode frequency, and at the end all of the masses are moving in the out of phase mode. And exactly the previous one, we sweep the frequency from 0.5 to 2.5, we can see how the masses are changing over here. So at 1, the phase difference of the masses along the chain and across the chain is near to 0, but when it moves to the second eigenmode, which is around a square root of 2, over there we can see the phase difference across the chain is has become pi, but the phase difference along the chain is moving to pi, then it again moves to 0, and it continues till square root of 3, and square root of 3 it flips. That means the phase difference across the chain moves to 0, and phase difference along the chain moves to pi, and so it continues till square root of 3, and after that one the masses from the driving frequency of 2, the phase difference of both of the masses, it becomes completely pi. This system can also be tuned by changing the damping of the system, the eta, and for that we can get from the all of the eigenmodes from by sweeping the frequency and applying forces in 2 of the masses, that means the first mass of the each of the chain. Now we calculate the superposition of a state in a mass chain, couple mass chain system. So in order to get the superposition of a state's coefficients, we choose the amplitude coefficient associated with each of the product state. So here we express the system with this equation, where in the left one the C1, C2, C3, C4 are the amplitude of the masses response, each of the masses response. Phi is the phases of each of the masses at that instance. And in the right of the equation we can see the E1 AL and E1 AC. These are the eigenstates that we defined before. Eigenstates, AL is the along the chain, that means in the from left to right, and AC is the across the chain, that means from top to bottom. Similarly, E2 AL and E2 AC are also the eigenstate for the same along the chain and across the chain. If we simplify the equation, we get the equation like this, and from here we can calculate the all of the amplitude coefficients. So here we can see the amplitude coefficients A11, A12, A21 and 22 here, and we can get the separable states or the pure states at each of the eigenmode frequencies. That means 1 square root of 2 square root of 3 2. Over here we can see the in the top only one of the amplitude coefficients, they are dominating in each of the eigenstates. So this is the these are the complete separable states. But if you want to see the non-separable states or the entangled state, where and how to see which one is the maximum entanglement state, to visualize this one we need the entropy of entanglement. So what is the entropy of entanglement? It defines the degree of the entangled state in each instances, and this is a fundamental feature of any quantum states. So in order to calculate that, we see the displacement state vector, which this is the displacement state vector, and omega n is the frequency that the system is currently vibrating. So we can get this from the FFT that we have, and this is the density matrix. Rho is equal to this one. To get the entropy of entanglement, we reduce the density matrix by taking the partial trace over one subsystem. Trace is the summation of the diagonal of any of the matrix. We use the partial tracing of the system, and from there we get the rho 1 and rho 2, which is the reduced density matrix. For entangled state, the reduced matrix, the entropy of entanglement for both of the reduced partial stresses will be similar, and from this we can get the entropy of entanglement. And as we can see from the bottom right figure, where for each of the pure state we have the minimum entropy of entanglement, that means 0. So here the system is completely separable. All of the pure states are over here, but in the case of this point, which is around 1.55, here the system is maximum entangled. The system is very highly non-separable. As we can see also, it is at this point. So with the entropy of entanglement, we can see how the system is moving from a separable to a non-separable state. Now we are moving to the nonlinear coupled mesh system. So in order to revise a nonlinear coupled mesh system, both theoretically and experimentally, we choose the granular beads. Granular beads are highly nonlinear due to their single point contact between the beads. They are highly adaptable to the any external applied amplitude or applied frequency. We can easily get different responses just by changing any of the either the amplitude or the frequency, and we can move from a nonlinear system to a linearized system just by applying the static preloading in the system. The static preload, with the higher amount of static preloading, we can get the higher linearized system from the nonlinear coupled system. So in order to develop the nonlinear system equations, the general mathematical expression we get is as this one, the top equations, where the delta naught is a static preloading. This static preloading can make the system from nonlinear to linearized system, and if this is higher than the relative displacement of the granulars, we can do the power expansion of the Taylor series, which we can analyze for the case of how much nonlinearity we have in the system. So now we have all of the equations that is nonlinear system for the nonlinear equations over here. So this nonlinear equation, we can see we are driving only one of the masses. This system can be made linearized just by applying the higher precompression, so that like this, and from there we can make the system as a linearized system. And through calculation, we can see that linearized system depicts the linearized in phase and out of phase mode, which we got earlier in a linear system. So from a nonlinear system, just by changing the static preloading of the system, we can get the linearized in phase and out of phase mode. And from there, the complex amplitude field for the linear system, we can get the alpha and beta, which are the complex amplitude coefficients which depict the superposition of states of each of the system. Now if we want to see the nonlinear response of the granular bits of two mesh system, we can see that both of the two in phase nonlinear normal modes and out of phase nonlinear normal modes. In the in phase out of normal modes, we apply some static preloading. This is a numerical simulation. We apply nodes static preloading. We apply omega d equal to 0.44 and some amplitudes over here. We apply some viscous damping. So we can see that this is a highly nonlinear system with the in phase with both of the masses. So in case of any nonlinear system, we will see multiple peaks in the fast Fourier transform or FFT. So we can see the system is vibrating at multiple frequencies. This one is 0.44, this one is 0.88, which is just multiple of the driving frequency, 0.88, and so on. We can get 1 omega d, 2 omega d, 3 omega d, and 4 omega d. And we can see the from the dominating peak. Dominating peak is the where we have the phase difference of 0, which depicts this is an in phase NNM. And in the second case, as the system is non-linear, for the second higher response or second peak, we can get the phase difference as pi, and so on. This line shows the 1% of the 1% of the maximum peak. As we are in order to eliminate noise in the experimental simulation, or over here we eliminate all of the noises. So this is an in phase NNM, and in the case of the out of phase NNM, this is an out of phase system where we are driving the system in another frequency, omega d equals to 0.73, where the system is moving in out of phase. As the system is non-linear, we still see multiple peaks. So this peak is 0.73, and this peak is depicting the 1 point. It's depicting the 2 omega d, which is around 1.46 to omega d. So in the max highest peak is showing the phase difference of pi, which depicts the out of phase NNM. So now we move to the nonlinear response of the two mass two chain system. These are the nonlinear system where we apply a same frequency, but we apply different amplitudes in the two of the masses external excitation. So in this one we are applying a1 equal to positive value in both of the cases, but over here we are applying different values, out of phase frequency, external excitation amplitude mode, where we can see that this is the in phase NNM. Same case, in phase NNM, all of the masses are moving in the same direction, but over here we can see the two of the masses are moving in the in phase, which is along the chain, but across the chain they are moving out of phase mode. And similar case with the FFT, we can see multiple peaks, as this is a non-linear system, and for that we can get different types of phase difference all at once. So we are getting at the dominant frequency all of the phase across the chain and along the chain both are 0, but in case of this one where we are driving the system in out of phase mode, where out of phase NNM, where we can see the along the chain the masses are moving in the in phase direction, but across the chain they are moving in the out of phase direction. We can see the their maximum peak is at the driving frequency of 0.41, but the second peak is at the 2 omega d of 0.82. Now we can calculate the superposition of states coefficient alpha and beta t. In order to do that, we take the orthonormal basis of the two mass granular system. Here we are calculating the nonlinear superposition of states, which is time dependent. In the case of linear system, the superposition of states is always constant. That means they are time independent. But for the case of the nonlinear system, as the system is vibrating at multiple frequencies all at once, we can get a time dependent superposition of states. As we can see over here, phi u1 is the masses phases at each of the time, and u1 n means that how many peaks that we have, which is the 1% of the maximum peak that we have and from there we can get the superposition of states coefficients, complex amplitude coefficients alpha t and beta t, and just by normalizing the value, and from there we can get the complex amplitude coefficients alpha t and beta t, and from there we can say get the state vector of the system, which is psi equal to alpha e1 and beta e2. So when the system is in phase mode, then only alpha will dominate. That means alpha will have maximum value and beta will have minimum value. But when the system is vibrating at any out of phase mode, that means e2 mode. So e2 at that time beta will be maximum and alpha will be minimum, and we can get pure states at these two instances, and this two level subsystem represent the elastic bead, which is isomorphic to a qubit. Now we move to the experimental demonstration of the classical analogous superposition of states. So in order to do that, we devise a system experimental setup, and in this setup we can see that that two granular beads are in contact with each other, and we use two transducer to hold the system. Also one of the transducer, the right transducer, this one is vibrating the whole system from in a frequency range. We set the amplitude to a constant value and we vary the frequencies, but we can also do other way around. That means we can fix the frequency and also change the amplitudes. This transducer is driving the system. This transducer is recording the response, but it is the main purpose of this is to hold the system, and the top two transducer are our recording transducer. So this in order to record the responses, we put the two transducer with the tape with to get the same amount of peak compression for these two transducers, and there are honey that are applied between the transistor and granular beads in order to suppress all the vibration that is coming from out of the system. All the transistor these two transistors are connected to an oscilloscope to record the responses, and this transistor, the driving transistor, is connected to a function generator which is connected to another amplifier to drive the system at various frequencies. So now we can measure the response that we have. So at the driving frequency of 9.85 kilohertz, we get an in phase near in phase mode that we have. So in this is the response that we have in the top one. In the bottom we can see the frequency FFT of the system, where we can get the maximum peak at 9.85 kilohertz, and the other peaks are this one is a 2 omega d, this one is a 3 omega d, this one is a 4 omega d. This lines means that we are taking only 1% of the maximum peaks in order to reduce the noises that are coming from the system. Now we can see that in the maximum peak the phase difference is 0, which is depicting the in phase mode. That means the system is moving to a near in phase mode, but the system, as it is a nonlinear system, so we can get multiple frequencies. From the second highest peak we can see that we have the another frequency which is around 80 degrees degree over here. So from this we are getting multiple of the peaks that we have, and multiple phase differences between the masses, and we can get a out of phase mode from in the driving frequency of 9.05 kilohertz, where we can see the maximum peak has an out of phase mode of around 180 degree, but as the system is has multiple is a nonlinear system, it will have multiple driving multiple frequency ranges. That means we have another which is 9.05, this one is 2 omega d, this one is 3 omega d, and in those responses we can get different amount of different types of phase differences. So over here we can get around 30 degrees Celsius, 30 degree, or in the right we can also get the 30 degree phase difference over here. So now we move to the time dependent complex modulus, that means alpha and beta, how the system is behaving at the alpha and beta. So as the first system is moving in in phase mode, we can see the alpha is dominating in each with time, and beta has a lower value than the alpha. So as the system is moving in phase mode, so that means the closer it is to the pure state, the higher value of the alpha we can get. But the system, as it is a nonlinear system, the alpha does not dominate completely with other amount of phase differences that we have, like around 2 omega d. This system becomes a time dependent complex modulus, and it has dominating alpha but not completely dominating. That means not completely alpha has highest value. But in the case of the 9.05 kilohertz, the system has higher nonlinearity than the previous one. That means the system has both the pure state completely completely non-separable state at one time, and a amount of close to the pure state at another time. As this one is the beta is dominating than the alpha, that means it is closer to the E2 state at this time period. But at another time at this time instance, on this region, the system is a completely non-separable state. So with the same amount driving frequency and amplitude, we can see that the system is moving from a very highly non-separable state to a closer to the pure state, which is E2 state, as the beta is dominating over here. Now we will use Hadamard gate operation in the experimental result of the nonlinear granular system. So Hadamard gate is a fundamental quantum gate in quantum computing. It operates on a single qubit and transforms it into a superposition of basis states, enabling quantum algorithms to create and manipulate quantum superpositions efficiently. To demonstrate the Hadamard gate system, we first need to apply understand the blocksphere of the system. So what is a blocksphere? The blocksphere is a system that can show the position of the states, pure states, and also the superposition of states in a three-dimensional geometrical sphere. So in order to get that, we need the two of the parameters of the blocksphere parameters, theta, which is a polar angle, and phi, which is the azimuthal angle. And with our superposition of state system, we can get the theta and phi through the alpha and beta. So here we can see alpha is the cosine theta by 2, and beta is the exponential of I phi sine theta by 2. And from there, here we can get the theta and phi from these equations, where theta is the inverse cosine of alpha, absolute alpha into 2, and beta is the phase in the phase difference between the superposition of states coefficient alpha and beta. And now we take two instances. So at time t1, we can see the system has beta is maximum, and at that moment we can say the system is closer to the E2 state. And we take another time instance which is t2, which is which is closer to the maximum non-separable states. So we can take the time t1 and time t2 and apply the unitary transformation matrix, and we can see the gate operation from one time instance t1 to another time instance t2. And this Hadamard gate is also reversible, so we can get the same response just by reversing the gate operation at the superposed states. And this transformation matrix is the usual Hadamard gate. So from here we can say that we can easily move from one state to another state without changing any kind of external parameter like the frequency or the amplitudes. Now we move to the Berry connection and the Berry phase in the system. So why we need the Berry phase? So what is the Berry phase at first? When the system is subjected to change any to a subjected to change in cyclic adiabatic processes which result from the geometrical properties of the parameter space of the Hamiltonian, the Berry phase is the phase difference that is accumulated over that cycle. We can characterize the behavior of the elastic beads through the Berry connection. The driving parameters which are discretized for a finite number of bits, and the Berry phase connection can be calculated through those parameters. For our elastic bead, we can calculate the accumulated phase difference using the amplitude of the beads, the complex amplitude of the superposition of states, and the blocksphere angles. In our research study, in the previous studies, the amplitude of beads and the complex amplitude of amplitudes of beads are explored in spectral analysis of the amplitude and phases. But in our study, we are focusing on the complex amplitude of the superposition of states and on the blocksphere angles, as the blocksphere angles demonstrate the superposition of states very clearly with the blocksphere or in a three-dimensional geometrical sphere. So from there we can see the Berry connection as this equation, where we can see it has multiple amount of points. Theta is one point, and theta plus delta theta is another point. For a linear system, we can take two different frequency or any other driving parameters to see the changes between one point to another point. And in nonlinear system, we can take the theta as a time, as the theta will be time dependent. We can move from one theta to another theta for a single frequency or amplitude, and move from one time to another to get the Berry connection. Berry connection. So here we are calculating the Berry phase of the system. The Berry phase according to the polar and azimuthal angle, it becomes like this, where we get the inverse of the state vector psi and take the first derivative of the state vector psi, and from there we can get the Berry phase of the system. Gamma is equal to -1/2 into phi final minus phi initial into 1 minus cosine theta. But this equation is only applicable when the theta is kept constant. That means the system superposition of states is at a constant distance from the from the z-axis, which is formulated by the theta, and it is moving along the Bloch sphere just by the changes with the azimuthal angle phi. But in order to calculate the Berry phase of the system for a varying theta also, we need to formulate the Berry connection of the system, the Berry connection that we got earlier. And from here, with the bottom equation, this one gamma, we can get the Berry phase of the system for when the theta and phi both are varying. Now, in order to model the granular network and get the Berry phase of the system, we need to first formulate the linearized system as we got earlier. From there, just by calculating the amplitude of the system for a linearized system, when the system linear responses is constant with time, so we can get the amplitude of the system A1 and A2, and using the A1 and A2 we can get the superposition of states coefficients alpha and beta. As the system is a linearized system, the coefficient of the states become alpha and beta like this, and which is time independent, and it only moves along with the external force that we apply, F1 and F2. And so from there we can get the polar angle and azimuthal angle as theta and phi, and we can get the state of the system, which is expressed in a qubit. So this qubit expressed in a qubit with the Bloch sphere angles theta and phi. From here we can see when the theta is 0, then the system is in a pure state of E1, and when the system theta is pi, the system is in pure state of E2. So from here with the linearized system, we can also get both of the pure states. And in order to study the Berry phase and hence the topology of the system described, we have to apply the external excitation, and from here we can see the F1 and F2, which is the amplitude of the external excitation. Here E1 by E2 is the state ratio, that means the how much state we are giving in each of the amplitude of the forces, and delta is the initial phase of the system, that means how much phase we are giving in the driver. From here we can see the response of the system for the case when we are evolving the E1 A2 and keeping the initial phase of the system constant. The left one when we are system keeps the system initial phase as pi, and the right one is when the initial phase is kept at pi by 2. From here we can see the system is moving, starts to generate from the pure state of E2, and it moves to a superposition of states, and then it moves to the E1 state, and we can get a same response in the second figure also. But with the change of the initial phase, we can revolve around two different planes. In the next case, which is where we are revolving the initial phase delta, but we are keeping the state ratio constant. The left one when we are keeping the state ratio as 0.5, and the right one where we are keeping the state ratio as 0. So in the left one we can see that we are keeping the theta constant and revolving the phi a complete 2 pi revolution. But in the right we can see we are keeping the azimuthal angle phi constant, but we are revolving the polar angle theta to a complete 2 pi revolution. Now how we are changing the evolution of the Berry phase with the external excitation and with the frequency. Here we are keeping the state ratio E1 and E2 to a constant value, and we are then revolving the initial phase from minus pi to plus pi in each of the cases, and for different value of driving frequency, we can see how the system is moving. That means when the E1 E2 ratio is at 0 for the system, when it is driving on 1, we can get the initial phase of Berry phase of pi at when the E1 E2 ratio is 0 and frequency is at 1. But when the E1 E2 ratio is at 1, we can get the Berry phase of pi when the system is driving at the second eigen mode, that means omega 2 equal to square root of 3. This is an evolution. As we can see, we chose in most of our cases, in most of the cases that we have in the later one we chose the square root of 2, as this one gives us at the state ratio of 0.5 we can get the Berry phase non-trivial Berry phase of pi. We have two of the Berry phases, trivial and non-trivial. Trivial Berry phase is the Berry phase of 0, and non-trivial Berry phase is the Berry phase of pi. And in the later driving frequency and then the previous responses, we always are seeing the keeping the driving frequency at a square root of 2. So here we can see at different instances when we are driving the system at one state ratio and revolving the delta, how the amplitude of the masses are changing. In the left plot figure we can see over here the when the system is we are keeping driving the system with the initial phase of pi. So at that instance the mass 1 has the highest amplitude and mass 2 has the lowest amplitude of 0. That means only one of all the energy of the drivers are stored in the mass 1, and when the system is moving at delta is equal to 0, that means at that moment all the energy is stored at the mass 2, and mass 1 does not have any energy and it is not vibrating. But if the system is moving at we are driving the system with E1 A2 as 0, we can see at any instance of the initial phase the masses have the same amount of amplitude, and energy is stored equally in each of the masses. In the bottom figure we can see what is the phase difference of the two of the masses, and also what is the phase difference between the one of the masses and one of the drivers. So with the increasing amount of state ratio we can see at the systems increase amount of E1 E2 is changing the zone of the each of the phase of the masses and each of the phase of the masses and drivers. That means when the phase difference is 0 for the both of the masses at this point, when the state ratio is very low, at that instance the phase difference between the mass and the driver has the highest phase difference of pi. So with the increase of the state ratio we can say that all of the zones are changing their position in these two instances. So now we move to the quantum gate operation for our granular network. So in this case we are plotting total of 6 of the quantum gates. So in the quantum gates, basically what it does, it moves it changes the state of the system to one state to like one pure state to another pure state, or one pure state to one superposition of a state, or one superposition of a state to another superposition of states, without changing any kind of driving parameters like the external excitation amplitude or external excitation frequencies of the system. So at first we can get the we choose one pure state of E1 state. At that moment this is the point of the states. So the first one we get the Pauli X gate. What Pauli X gate does, it moves one pure state E1 to another pure state of E2 at in the positive in the real axis. That means in the x-axis this is a Pauli X gate. And then we have another if we take the same E1 state as E1 state, and we can move to the imaginary axis. This is called the Pauli Y gate. So the second one is the Pauli Y gate. And in the third one, what is the Hadamard gate? Hadamard gate moves the one pure state to the another superposition of states. So we are moving from one pure state to one superposition of states, which is the Hadamard gate. And the next one we have the one superposition of states which is on the E1 plus E2. So this is moving one pure state. If we take the E1 plus E2 divided by square root of 2 as an positive superposition of a state, it moves one positive Pauli Z gate moves one positive superposition of a state to the negative superposition of a state of the system. Now if we move to another state which is called the phase gate. So the phase gate, what it does, it moves one superposition of a state positive state to the another linear combination of the states. So if E1 plus E2 divided by square root of 2 is one linear combination of states, another linear combination is E1 minus E2 divided by square root of 2. Phase gates moves one linear combination of the superposition of states to another linear combination of the superposition of states, or superposition of states. Now we have another gate which is called the T gate. T gates moves the gate to a pi by 4 angle. So that means it moves moves one superposition of state to a angle of pi by 4. So if we want to see all of the states, so these are the all of the states. So we have Pauli X gate, which is moving from one pure state to the another pure state in the in the real axis. Pauli Y gate is moving on the imaginary axis, and so on. Pauli Z gate, Hadamard gate, phase gate, and T gate. So these are all of the gates that we can obtain from the granular network, and we can move from one state to another state without changing any kind of external excitation. That means we are not changing any state ratio of E1 by E2 and or the initial phases or the frequency over here. So we move to try to calculate the Berry phase of the system for a nonlinear system. So in order to formulate our theoretical calculation, we take a total of third order nonlinear system, and in order to see what is the amplitude of the system, we take the displacement field as this bottom one, u1 equal to u1 0, like this, and where this epsilon is the order of the stiffness of the coupling. That means k1, k2, k2, k3, this value, this is the order of the system for the coupling and for the displacement field u1. So from there we can get the all of the amplitude of the system, and later we calculate the system. So we chose some specific pre-compression, driving frequency, and the amplitude of the forces F1, F2, and some viscous damping. And using the perturbation method, we can get the multi-scale perturbation method. We get the change of the modulus of alpha and beta with different concerning time. As we can see here, alpha is dominating than beta, so this is a close value to this is a closer response to the E1 state. But in the second figure, where we are calculating the Bloch sphere angles theta and phi, we can see that while the theta is not constant, but it is closer to the constant value, but phi is changing from plus pi to minus pi. That means it is completing a total 2 pi of revolution. So from here we can calculate the Berry phase of the system. Now, as we have calculated the Berry phase of the system for the system, we can use this as an experimental demonstration of the mass sensor. We can use the Berry phase of the system in order to calculate the sensitivity of the system. So this is our experimental setup. So what we do, we at first we take the response of the system without any kind of mass defect added in the system. Later what we do, we add 3 of the magnets. These are very small amount of magnets, which is only 0.15% of each of the 2 of the balls, 15%, and 0.2 later we add 4 magnets, which is 0.2% of the granular beads. So we add this to response, and later we calculate the response of the system. We are still working on the on this experimental demonstration of the mass sensor. So we are working on that to calculate the sensitivity of the system using the Berry phase. But here are some of the responses we can see. So we take the phase difference of the superposition of state alpha and beta. For 0%, that means no mass defect, then 0.1% and 0.2%. We can see there are some changes in the response of the system, and later what we calculate the difference between each of the points and see how much response it is creating in the with respect to the time. So here we can see for 0.15% there are some jumps, and with the addition of the more mass defect, the jumps diminishes over here. And we can see where the difference between this 0.15% 0.2%, there are some changes for, which is around 2 it starts from minus 1.9 to and moves to around 1.5. So there are some changes in those regions. We are still working on the mass sensor and try to calculate what is the sensitivity should be in our system using the Berry phase. And we have also studied about the amplitude and phase characteristics of the elastic waves using the superposition of states. So in this case we have two mass system where we have where we take a granular network, and we have two of the coupling. That means each of the masses have different different springs that is connected to different spring stiffness, and using this stiffness we take the solution of the traveling wave as u1 ni, u2 ni, and we can calculate the a1 and a2. And for two different cases, for psi 1 and psi 2 we can get two different types of amplitude responses. That means when psi 1 is greater than psi 2 and psi 2 is greater than psi 1, and we use this using the periodic condition. We calculate the amplitude of the network. After calculating the amplitude of the network, we calculate the state of the superposition of state, and visualize the system in the block sphere angles. As we can see, we can explore a large amount of states when we are moving the system in a psi 1 less than psi 2 manner. That means mass one of the spring that is left of the first mass connected, it is higher than the later spring spring and with that we can explore a higher amount of states. As we can see, it is moving on a total one plane, but over here we can see it is moving only half of the plane. And we can see in the case of psi 1 less than psi 2, psi 1 less than psi 2, it is creating a twist over here. This twist of the superposition of states alpha and beta. So we can get a higher amount of states when psi 1 is less than psi 2. Now we calculate the Berry factor and Berry phases. As we can see in the Berry factor, in both cases of the stiffness relation psi 1 greater than psi 2 and psi 1 less than psi 2, the real value is always 0, and it has some value in the imaginary cases of the Berry factor that we calculate. So over here in the bottom one, we can see how the Berry phase is accumulated. So in the when psi 1 is greater than psi 2, the Berry phase accumulation is total is a 0. That means it starts from 0 and it ends to 0 when the wave number is at 0 position, and it moves again to 0. And as the phase accumulated over the period is 0, then the Berry phase is 0 in case of psi 1 greater than psi 2. But when psi 1 is less than psi 2, we can see the block sphere angle theta and phi, it is moving from pi to 0 and then again to pi. That means over the period it is accumulating phase difference of pi. Then we move to the time dependent stiffness. Why we move to the time dependent stiffness? As we can see from the previous block spheres, we can see we are only moving the states in the only one of the planes. That is, it is not moving in the total block sphere. So we take a time dependent stiffness, and from the previous study of Dr. Hassan, we have taken the spatiotemporal modulus, and we calculate the band structure of the time dependent stiffness system. So here we can see this is one of the first fundamental branch and second fundamental branch. We calculate the superposition of states using the first fundamental branch, and we can see there is a twist in the case when it is in the case of psi and minus, and the second one is and the first one, this one is depicting the psi and plus, and second one is depicting the psi and minus. So in the case of psi and minus, it is creating a twist. And if we see the block sphere of the system, we can see all of the states are moving in all of the spheres. That means it is moving. We have a much amount of flexibility in the states, and much higher amount of regions are explored in the block sphere if we can move to the time dependent stiffness. So in our total research studies, we analyze the superposition of a granular beads in both theoretically and experimentally. We have analyzed the pure states and the superposition of states using the complex amplitude coefficients alpha and beta. We have demonstrated the preparation of the classical analogous quantum superposition of states is in a nonlinear granular system. We have also demonstrated to manipulate the coherent states in time uh, without the external drivers amplitude and frequency, which is in a equivalent to the applying the gate operations. In particular, in Hadamard gate, which we have shown in a experimental demonstration of the nonlinear granular system, and with the nonlinear granular system, that we can explore the whole nonlinear system, just not by the frequency, also by tuning the amplitude of the system. And we have also shown the theoretical conception of the Berry phase using the superposition of states, and when mapped onto the Bloch sphere, the states vector trajectory of this elastic bead in a parameter space, we can precisely manipulate using the external drivers amplitude, phase, and frequency, which result in a specific Berry phase. And we have also shown that the elastic bead displays the trivial and non-trivial topologies. So the we can see the zero phase, which Berry phase correspond to the pure states, and any superposition of states can take values which is defined from 0 to 0 or pi. Moreover, such phases correlate with the structure's eigenmode vibration. The trivial phase aligns with distinct in phase and out of phase eigenmodes. We have also demonstrated the Berry phase in order to devise a mass sensor which has a higher sensitivity than the conventional sensing methods.